Hey folks, this is the first video for today's lesson. Sorry I can't be with you today, but I did want to make sure we had time to go through everything that we've been talking about, make sure that you're comfortable understanding what it is we've been discussing. This worksheet, some of the problems were pretty basic, but some of the problems some people had questions about did involve a little bit of higher level thinking, joining some of the ideas we've been talking about together through the ideas of Newton's laws, the formulas for Newton's laws, combining those with the old acceleration problems. So if you start out here, I cannot make this any larger. You should have your sheet in front of you, just so you know. But starting with the first question, what's measured in a unit of a Newton? That is force. When you measure force, you measure that in newtons. What does a Newton break down into? It's an abbreviation for which units. That you should have been able to get from your notes. That was just kilograms times a meter per second per second. Remember, meters per second could also be written as meters per second squared. So you could have also written kilograms times meters over seconds squared. That's going to come up when we break newtons down, and you have to divide by kilograms or meters per second, and you'll see what cancels out and what's left. So we do want you to have that memorized, that a newton could be broken down into this. 1 newton of force is defined in your notes as the amount of force it takes to do what? Now I'm not going to write that all the way out, but if you do recall, we said that that will be on the test. We want you to understand how much of a force is a newton, and it'll make 1 kilogram accelerate 1 meter per second faster every second. As a matter of fact, if we go back to your notes from last class, we had this little illustration here showing that if you have 1 kilogram and you pull with a net force of 1 newton, then you see the speed goes from 2 meters per second to 3 meters per second to 4 meters per second. Each second you're gaining a meter per second of speed. That is the definition of a newton, how much force it takes for 1 kilogram to accelerate 1 meter per second faster each second. So going back to this, according to Newton's third law, when a small object is hit by a larger object, which of these is true? And the answer here was the very last choice. Remember, Newton's third law says for every action there is an equal and opposite reaction force. In other words, when you push on something, the reaction force that pushes back on you is always the same amount of force. It doesn't matter what the size of the object is, how fast things are going. The forces are always the same when one object pushes on another. So they hit each other with the same amount of force despite the difference in size or mass. When we get down to the problems, the first problem talking about a truck being in an accident, being hit by another car. The truck has a mass of 2,500 kilograms. It undergoes an acceleration of 22 meters per second every second. In other words, it changes its speed by 22 meters per second for every second that it's being pushed by that force. So the net force required to make this happen, well, before we do that, it does ask us to make a sketch. Now, this one should be easy. As you go along, the problems are going to get a little bit more involved. You get a lot of information. You can't keep all that information in your head very easily. Therefore, we're asking you to go ahead and make the sketches. This one should be easy, so when we go to the harder ones, it's not trying to throw in a whole lot of information for the very first time and trying to figure out how to get all that stuff down. By starting you off easy, you can gradually work your way up to the harder sketches. Now, you know that I haven't been making a very big effort to make it artistic. We just want you to get the ideas down. So you can draw a car if you want. I'm just going to draw the box. And we said it has a mass of 2,500 kilograms. Now, even if I didn't say mass, if I just said it was a 2,500 kilogram object, you should at this point know exactly what we're talking about. If we go back to this slide, you should have this sheet. Remember, this is for your reference. And the column that we said that we're mainly using is going to be this one. And when we talk about mass, mass is measured in kilograms. We do want you to know that when you see so many kilograms, that it is talking about mass. If you see something in meters per second, we're talking about acceleration. If you see something just measured in seconds, we're talking about time. Make use of this sheet until those ideas get memorized and you don't have to use it anymore, but it is there as a tool. Please don't forget about it. So as we said, you've got your mass of 2,500 kilograms, so we go ahead and write that. Let's choose a better color here. So mass of 2,500 kilograms. And then we have an acceleration of 22 meters per second per second. Now, we mentioned before, probably a good idea for the forces to be attached to the box, but the velocity and the accelerations you can draw below or above the box. If it's moving upward, you can do it from either side. So for the acceleration, we'll go ahead and mark that here. 22 meters per second is positive. We're going to assume that that's sideways, and positive sideways would be this way. So your acceleration, 22 meters per second. And it wants to know what net force would have caused this mass to have that acceleration. Now remember, the acceleration is always in the same direction as the net force. So even though we don't yet know what the net force is, we can go ahead and assume that the net force is in the same direction as the acceleration. So we're looking for this. When it's time to now solve for the problem, again, this one was easy to draw and set up. The first thing that we should do after you have everything labeled and you know what you have is to try to figure out which relationship you're going to use mathematically. Now you were given this triangle. And so we're looking for net force. We have mass and acceleration, so everything we need is right here. If you want to rearrange this all for net force, cover that up. And you see that mass and acceleration are next to each other. When they're next to each other, you multiply. If they're on top of each other, you divide. So for this one, we'll go ahead and write net force equals, cover that up, mass multiplied by acceleration. And so when you multiply your numbers together, you have 2,500 kilograms multiplied by 22 meters per second every second. And that answer comes out to be a total net force of 55,000. Now as far as the units go, you have kilograms and you multiply that by meters per second per second. So you can say kilograms multiplied by meters per second per second. Officially, those are the units for force. But recall that we discussed, instead of writing all of this, you could choose to abbreviate that in a one-letter unit, the Newton. So you may put this as your unit, you may put that as your unit. Either way is fine. You'll get full credit both ways. Just make sure you're starting to see that those two can be switched back and forth. 1C. Now you know the force of the car hitting the truck. So how hard did the truck hit back on the car? And we have a little friendly reminder here for you. Newton's third law says for every action force there is an equal and opposite reaction force. And so if the forces are equal, that means if the truck got hit by 55,000 newtons of force, then it hits back on the car with the same amount of force, 55,000 newtons. Now technically that's in the opposite direction, so I'm not going to count you off if you didn't do this, but since that's in the opposite direction, you would say that that is in the negative direction. We said you may skip 1D, and then we go on to 1E. So how hard? The car in the accident had a mass of 1,200 kilograms. If it was hit with the same amount of force through Newton's third law, then what would the car's acceleration be? So that we know two things here. We know that the mass of the car is 1,200 kilograms right here. Now with the truck, it had a larger mass. So you may already be thinking to yourself, if they're hit with the same force, but you have a smaller mass, what would that say happens to the acceleration? More massive things are harder to move, less massive things are easier to move and accelerate. So if they're hit just as hard, this smaller mass, we're going to expect to have a larger acceleration. And so we're asking you to do the math to see what acceleration you actually come up with. The other thing we said is that the force is the same. So the net force, it gets hit just as hard as it hit the other object. So 55,000 newtons. It is your choice right now whether you want to throw in the negative or not. So if we want to solve for the acceleration, which is what we're being asked to solve for, we go back up to that triangle. You cover up the acceleration, and now what's left? Net force is on top, mass is on bottom. Therefore, you divide the top by the bottom, and you end up with acceleration equals the net force divided by the mass. So you just plug in your numbers at that point. 55,000 newtons divided by 1,200 kilograms. And the answer you get, I believe, was 45. And if I check the answer key which we provided you in class, it rounds to about 45.8. The question might be then, to get full credit, you have to have the right units here. So what units would those be? Remember how we talked about right up here, it's not going to scroll up for me, that a newton is a kilogram times a meter per second per second. So if you replace newtons with this, hopefully you do see that the kilograms are going to cancel right out, and the only thing you have left is meters per second per second. So this is how much the speed changed every second. Since the car is being pushed in the opposite direction and it was moving, we can basically interpret this as the car went 45.8 meters per second slower every second it was being pushed with that force. Now, why would the larger acceleration, why did the car have a larger acceleration than the truck if they were pushed with the same force? And we mentioned that before. The car's acceleration was 1,200 kilograms, which, while that's a lot of mass, is not as massive as the truck. The truck was a larger mass, and you know that larger masses are harder to speed up, they're harder to slow down. So when you put the same force on both objects, the larger mass is going to have an acceleration, in this case of 22. But this smaller mass, it's easier to accelerate. So when you put the same force on it, it'll accelerate more quickly. And it has a larger acceleration of 45.8. So basically what we're looking at here is the smaller mass is easier to accelerate, and therefore the same force caused a larger acceleration. That's why the accelerations are different. Now if you flip to the back page, we mentioned to you that we're not just doing force equals mass times acceleration. This assignment was a little bit tougher because you had to combine your older formulas. And if we look at the formulas that both involve acceleration we've seen so far, you've got today's formula, net force equals mass times acceleration. But you also have your older one where the acceleration is the final speed minus the starting speed, initial velocity, divided by the time. And what we were trying to get you to see here is if they both involve acceleration, then it turns out that these are not exclusive to each other. There's a relationship between finding acceleration this way and that way. So we want you to see that, yes, that was from a different chapter, but we want to continue to use those ideas. We want to build your ideas up. You're going to have more than one way to find acceleration now. You could take this formula and rearrange it to find acceleration this way. And if we know the acceleration there, well, we could have a situation where if you know the acceleration and the final velocity and the time, you could find the initial velocity. So for example, if you look up the formulas that we've had you write down, I could give you a problem where you know the force and the mass and you could find the acceleration. And once you have that acceleration, you could plug in a problem where we also gave you the final speed and the time and use it to find the initial velocity. So we want you to be able to combine these ideas together, to not think about them as totally exclusive ideas, but as different ways to look at a situation. The more ways you can look at a situation, the more ways you have to go about solving it. So if one approach doesn't work, you can work on another approach. So what we have here is a 40 kilogram person. They go from 4 meters per second to 13 meters per second, and they change that speed in 2 seconds. We'd like to know the person's acceleration. Now again, I'm not going to spend a lot of time making this really artistic, so even though it's a person, I could draw a stick figure. I'm just going to stick with my boxes. And so you've got the 40 kilogram person. Now I didn't say what that measured yet, but it was kilograms. Again, if it's kilograms, you can look at your list if you don't remember, but kilograms measures mass. So you've got the 40 kilogram person, and at that moment, they're going 4 meters per second, and then they speed up to 13 meters per second. So hopefully you recognize meters per second. Well, those are velocities. So we've got your starting speed, initial velocity, and your final speed, your final velocity. So if I were to draw this, I said you can, for the velocities, you can put them above or below the box. So we can just put it right up here and say, hey, we started out at a speed of 4 meters per second. Later on, we had the same object, but now it had sped up, and it's got a velocity of 13 meters per second. And then the last thing that we know here is we do know that it took 2 seconds for that to happen, and 2 seconds measures time, so we've got the time. So we actually have a little bit more information than we need to solve for acceleration. But if you take a look at your old acceleration formulas, you should see that the formula here would be acceleration equals the final speed minus the initial speed, or velocity, divided by the time. So basically, they go from 4 to 13 meters per second. When you do the math, the change in speed is 9 meters per second. And it took them 2 seconds to change that speed. The acceleration is going to say, well, then how much does their speed change every 1 second? So we plug our numbers in, and we get, remember, it's final minus initial, so you have to start with your final speed. 13 meters per second minus 4 meters per second. Divide by the time it took, 2 seconds, and that's 9 meters per second in 2 seconds. When you plug that into your calculator, you will get 4.5. And what that would be, again, is that's how much they sped up in a single second, which is the definition of acceleration, your change in velocity every second. So that was part A for the drawing. Part B, we did the math. Now part C, this is still the same problem. We know the acceleration, and we were told the object's mass. So once we found the acceleration and we already know the mass, we are now being asked to calculate the amount of net force. And looking again back at the formula, well, if we're looking for the object's force, you cover that up, that would be mass multiplied by acceleration. So in this problem, we now have the acceleration. We also have the object's mass, which right here we had drawn in our picture was 40 kilograms. And so we plug that into our formula. 40 kilograms times 4.5 meters per second. And what that tells us is you have an object with a certain amount of mass, which means it has a certain resistance to speeding up. So if you made it speed up 4.5 meters per second faster every second, you'd have to push with a specific amount of force to make that mass of an object accelerate at this rate. And when you plug your numbers in, actually, that should have been mass times acceleration, and the numbers go up here. So when you multiply those numbers together, let's see, that'd be 160 plus 20. So that looks like that would be 180. And you could write kilograms multiplied by meters per second. We did tell you that you could abbreviate that as the unit of a Newton. So most of you should be probably choosing to take the easier way and go ahead and call that a net force of 180 newtons. Now I'm going to make sure that I did the math right in my head, and that is what we came out with, so that's good. So there is the answer for 2C, here is the answer for 2B. So we're done with that situation. It's time to move on to the very last one, and we go ahead and scroll down. And so this last one is probably the most complex. We try to build your skills up to make sure that you're working your way to the level you need to be at. So this is talking about a rocket that's initially moving upward at 10 meters per second. So if I make that drawing, something simple. And the initial velocity is initially moving up at 10 meters per second, so we'd say the starting speed is 10 meters per second. It does say upward, so we're going to make sure we draw an arrow in the right direction. It's being pushed upwards with a net force of 525,000 newtons. So the force, pretty large. Might have trouble even fitting it right here if I'm going to write big enough for you guys to see. 525,000 newtons. And again, you don't have to, but it seems to make sense for a lot of people to attach the force to the object itself, because that's what's actually pushing it. The velocities and accelerations you can put on either side. Now it happens for 60 seconds. I've never been able to find a good way to show graphically what that would look like for time. So I usually just write my times off to the side, 60 seconds of time. And the last thing it says is it has an acceleration of 3.5 meters per second per second. In other words, it goes 3.5 meters per second faster for every second that it's being pushed with that force. So for the acceleration, I'm going to put that off to the other side and say acceleration is 3.5 meters per second faster every second. So we've got everything set up. It's time to go ahead and answer the question. The first one is, what would the mass of the rocket be? Now you only have one equation so far that solves for mass. And again, it's using that triangle, the force triangle. So we take a look at this and say, cover up what we're looking for, the mass, and what you have is net force on top, acceleration on bottom. So you take the top divided by the bottom, and your formula, net force divided by mass, or divided by the acceleration. Now, if we didn't have both those values, we wouldn't be able to do that. But if you made your drawing, you've got your force labeled, your starting speed, your time, your acceleration, everything's on there, and you should be able to see what you need. So far, we only have a few equations, so it's not as if you have a lot to choose from. It should be, at this point, relatively easy to find the right formula. Plugging those numbers in, we've got 525,000 newtons. We can make that look better. And the acceleration was 3.5 meters per second. At that point, you want to remind yourself the Newton does break down into a kilogram times a meter per second. So when you take these units and you divide by those units, we're hoping that you see that they do cancel out, at least the meters per second cancel, and all you have left is kilograms. So when you divide the numbers, you get the answer of 150,000, and then the units, after those items cancel out, all we have left is kilograms, so there is your units. And then the last part of the problem says, well, if that rocket was accelerating in 60 seconds, which we were already told that, then what would its final velocity be? So you started at this speed, you sped up 3.5 meters per second faster every second. So after 60 seconds, what final speed would you reach? Taking a look at your old acceleration formulas, you should be able to have one that solves for final velocity. And what that would look like would be final velocity is your starting speed, your initial velocity, plus the acceleration multiplied by the time. At this point, it's just a matter of plugging in your numbers and keeping track of your units so you can see if any of the units cancel. So our initial velocity was 10 meters per second. And then you sped up 3.5 meters per second faster every second. So after 60 seconds, you're going to gain a certain amount of speed. If I break this down piece by piece, this would be 10 meters per second plus 3 times 60 would be 180, and half of 60 is 30, so that would be 210. In other words, if you speed up this much every second, after 60 seconds, you would have gotten 210 meters per second faster. And if you're not sure how to get the units, You were dividing by seconds, and then you multiplied by seconds, so those cancel, and you're left with that unit. So here you go. You started at this speed, you sped up this much, so the final answer would be a final speed of 220 meters per second. So that is what we had for you, making sure that you understood what was going on with that worksheet. You combined a few different things. You had to understand the ideas of Newton's laws. You had to be able to use the formula for Newton's second law, force equals mass times acceleration, and we wanted to bring back the ideas from last chapter with the acceleration formulas to see how everything can be linked together into one large picture. So if you had done perfectly well and you understood that, well, you had already gotten this done. But some of the folks still had some issues, had some questions. Since I can't be here today to help you out, wanted to make sure we went through this. So hopefully this helps. We have some other things for you to take a look at. This is the end of video 1.